Okay, so in this video we are going to talk about molecular shapes, and we will use the VSEPR theory for this. VSEPR stands for valence shell electron pair repulsion theory. But before we get onto this, I think it would be better if we took a brief review of what we have covered so far. So we discussed why atoms make bonds. Atoms make bonds because they want to be more stable. And to do that, to gain more stability, they need to have electron configurations similar to those of noble gases. And noble gases, other than helium, has 8 electrons in its valence shell, and this gave rise to the octet rule, which says that while bonding, all atoms are trying to have a full octet in its outermost shell. Atoms can get an octet in its outermost shell in 2 different ways. One way is by complete transfer of electrons, and that give rise to ionic bonds. So atoms which are on the left side of the periodic table, they have very low electronegativity, and they very easily lose an electron, lose 1 or 2 electrons, and become positive ion. And likewise, atoms on the right hand side of the periodic table, they have very high electronegativity, and they gain electrons to get a full octet in their outer shell, and in the process they become negative ions. So positive ions and negative ions are held together by these strong electrostatic force of attraction, and that bond is basically known as the ionic bond. A covalent bond happens when elements on the right hand side of the periodic table try to bond with the elements on the right hand side of the periodic table. So both the atoms are on the right side of the periodic table, and both of them are deficit. Both of them have high electronegativity, so none of them is willing to give electron away. And in any case, both of these are 1 or 2 or 3 electrons away from the noble gas configuration. So they resort to sharing electrons, and when they share electrons, the shared electrons are counted by both atoms as their own, and both or more of these atoms, they are able to get a full octet in their outermost shell. This kind of bond is known as the covalent bond. Then we looked at the electronegativity and the bond polarity as well. We saw that if the difference in electronegativity is very high, then the more electronegative atom would very easily pull an electron away from the less electronegative element, and a complete transfer of electron takes place, and we get what we call as ionic bond. We get 2 ions, and the bond is ionic bond. But if the difference in electronegativity is not so high, then both the atoms have to share electrons, and when they share electrons, then it is a covalent bond. But even in covalent bonds, if there is a difference in electronegativity, we see that the more electronegative atom is able to pull the shared electrons towards itself, which gives it partial negative charge, and the weaker atom, that is the atom with lower value of electronegativity, become positively charged. So covalent bonds can be polar as well. We discussed bond polarity. So ionic bonds are very polar because you have a positive pole, a positive end, and a negative end. On the other hand, if you have bonds made between 2 exactly similar atoms, then both the atoms have same electronegativity, and the electron pair basically is located exactly in the middle, and the bond is totally non-polar because none of them is positive or negative. But if there is slight difference in electronegativity, then the bond is polar. The polarity of a bond depends, when we talk about a molecule, the polarity of a bond depends on the difference between the electronegativity. Bigger is the difference between electronegativities of bonding electron, more polar would the bond be. Then we also looked at electron dot diagrams, and we saw how an octet is basically represented with 2 electrons on 4 sides of atom symbol, and how we can use this to show bonding and all other things. With this, I think it would be also a good idea to do a very brief revision of these concepts. So we have two questions here, and I would suggest that you pause the video here and try to answer question number 1 and 2. So let's take a look at the solution here. So first one we got here is the bond between oxygen and hydrogen. We know that oxygen is on the right hand side of the periodic table, hydrogen is on the left hand side of the periodic table, and from the electronegativity table we can see that hydrogen has a lower value of electronegativity, oxygen has a higher value of electronegativity. So therefore oxygen pulls the shared electrons towards itself, which means oxygen become partially negative and hydrogen become partially positive. In the case of nitrogen and hydrogen, again it's the same thing. Nitrogen is more electronegative, so it becomes negative charge, and hydrogen become positively charged. 1C is a bond between chlorine and chlorine, and both the chlorine atoms have similar electronegativity, so this bond will be nonpolar. And oxygen and fluorine is the most electronegative element, and therefore it will pull the shared electron towards itself, and fluorine will become negatively charged and oxygen would become positively charged. Next question is a little bit tricky. It would require you to do some thinking. So here we need to order these 4 bonds on a scale kind of thing. So we need to, on one hand of this scale we will have ionic compounds, ionic bond, and on the other extreme we will have non-polar covalent bond type. So first let's look for an ionic bond. We can see that sodium and fluoride, that's our ionic bond. So that's I have here sodium and fluorine, because sodium is on the left side of the periodic table, fluorine is the most electronegative element, the difference between them is very high, so a complete transfer of electron would take place between the two. On the other end we are looking for a non-polar covalent bond, and I can see that bromine here, bromine, similar atoms, so we will have non-polar covalent bond of bromine here. So this is my scale. On the left hand side I got very polar bond, which is ionic. On the right hand side I got a non-polar bond. Now these other 2 remaining bonds we need to place in between. So we need to see where is the difference between electronegativity the bigger in these 2 cases. So in both the cases, one atom is nitrogen and the other atom is fluorine in one case and bromine in the other case. Now fluorine is the most electronegative of elements, so obviously the difference delta electronegativity would be higher in this, so this bond would be more polar than this bond, and that's how then I'm going to arrange my bonds. With that revision out of way, let's look at this valence shell electron pair repulsion theory. So we start with this. Let's say that I have a sphere here, and there are 2 sticks attached to the surface of this sphere. And just imagine that these sticks are free to move along the surface of this sphere here, and they repel each other. So because these sticks are free to move along the surface of the sphere, they would reorient themselves. They would try to get as far away from each other as possible, and finally they will settle in this shape. That's your sphere, and one stick will be here, other stick will be here, because they are trying to get as far away from each other as possible. Let's continue the discussion and see. Suppose we have, instead of 1 stick, instead of 2 sticks we have 3 sticks, and again these sticks repel each other, and these ends of the sticks are free to move on the surface of the sphere, and because the repulsion between these 3 sticks, they will end up as far away from each other as possible, and what we would get would be a shape looking like this, and each of these angle will be 120 degrees. Okay, let's look at third case here. Suppose I got 4 sticks here. Instead of 2 and 2 or 3, I got 4 sticks, 1, 2, 3, and 4. So when these 4 sticks, again these 4 sticks are, these 4 sticks repel each other. So they would reorient themselves, and many of you would be of the opinion that these 4 sticks would end up like this in a plane. But we need to keep in mind that this is a 3D shape. This is a sphere is a 3D, so sticks can move anywhere on the surface of the sphere. So this is not the surface that this is not the arrangement that you would get. What you would have is a tetrahedral shape, which is basically a triangular pyramid. Let me try to draw it here. That kind of triangular pyramid. So that, and that. And at the center you will have your sphere, and all the 4 sticks will be along the corners of 4 corners of this tetrahedral. I got a better diagram, better picture here to show you, so we'll just take you there for a moment and then we'll come back here. So this is what a tetrahedral look like. Here you got these 4 corners, and your sphere is in the middle here. That's a sphere in the middle here, and the 4 corners, your 4 sticks will go along the corners of these sticks. And if you find out the angle between any of these 2 sticks here, it will be 109 degrees. Okay, with that done, I think we can move to proper theory here. So as stated here, valence shell, electron repel, all these sticks that we have discussed are nothing but electron pairs. This is electron pair, that is electron pair, so the electron pairs repel each other, and that's why we have pair repulsion. So these electron pairs, they repel each other and they end up in this configuration. Okay, let's look at a few examples of shapes of molecules. So first let's take the case of methane. So methane, first thing we need to do is we need to draw its electron dot diagram. So electron dot diagram of methane is like this. Carbon needs 4 electrons to share, and hydrogen can share 1 electron only. So this way carbon ends up with 8 electrons in its valence shell, and hydrogen ends up with 2. So we got, in this particular case, we got pairs. How many electron pairs do we have? Obviously we can see that there are 4 electron pairs. So these 4 electron pairs, they are just like sticks in our previous example. These electron pairs, they repel each other, and as a result, all these 4 pairs, they will end at the 4 corners of a tetrahedral. So the shape of methane molecule is tetrahedral. Not able to, it's not clean writing, so this is that's a tetrahedral shape, and this thing has been experimentally verified. The angle between 2 hydrogen atoms is 109 degrees. Let's look at other example of water. So let's draw electron dot diagram of water first. We know that electron dot diagram of water looks like this. Then you have 2 lone pairs here. Just remember, I just use the terminology that we learned in previous videos. That is a bonded pair, and here this is a lone pair. So let me ask you, how many electron pairs are there in case of water? So some of you would say that there are 2, which is not right. When we are talking about electron pair, we need to take into account bonded pairs and the lone pairs both. So here, in case of water, you got 2 bonded pairs, this and this, and 2 lone pairs, that and that. So total number of pairs is 4. So again, as discussed in continuation to our earlier discussion, because there are 4 sticks, these 4 sticks will point towards the 4 corners of a tetrahedron. So what we will have in case of water is that you got O here, you got 1 here, you got 1 here, and then you got 2 other electron pairs here. Now these are lone pairs here. These are lone pairs. That's a lone pair, that's a lone pair, and these are a bonded pair. So when we look at the molecular shape, we are not interested in looking at these electrons here. What we actually see in a microscope or other way of seeing at molecules is this kind of, we only see the atoms. So when we look at this water molecule, we will see that it looks like this, and we call it V shape. So water molecule is V shape. You would expect the water molecule, this angle to be 109 degrees, but this angle is not 109 degrees, 109.5 degrees. This angle is actually 104.5 degrees. So what explains this? Here we need to take into account the strength of repulsion between different kinds of pairs. So your repulsion, strength of repulsion in decreasing order is this. So lone pair repulsion is the strongest one, then lone pair, bonded pair is bit weaker, and bonded pair repulsion is the weakest repulsion. So when we take this into account here, we find that, I come back to this water molecule here. So this is my lone pair, this is my lone pair, so the repulsion between them is too strong. This is the strongest repulsion between these two, so which means these two sticks will be pushed farther away from each other. Why? Because on the other side the force is not so strong. So this is my LP, that is my LP. They push each other away too much, and this repulsion also is bit stronger, and this is weaker. So end result would be that this hydrogen, this stick and that stick, this stick and this stick, they will come a bit closer to each other because these lone pairs are repelling everything around them. As a result, this angle between hydrogen, this angle between two hydrogens is 104.5 degrees in place of 109.5. Okay, that's my example number 2. So just to recap, that methane has a tetrahedral shape and water molecule has a V shape. Next is we look at ammonia, which is NH3. So first thing you always do is you need to draw the electron dot diagram. Very important. So we know that nitrogen has got 5 electrons in its outermost shell, so it will share 3 electrons with hydrogen, and there will be 1 lone pair. So again, just like the previous case, we see that total number of electron pairs is equals to 4, lone pairs is equals to 1, that's the lone pair here, and bonded pair is equals to 3. Okay, so again the shape would be tetrahedral. These 4 sticks consisting of these 4 pairs, or call them 4 sticks, this lone pair and 3, they will all point towards the corners of a tetrahedral. But just as discussed in the previous case, what we have is we have this lone pair here sticking out, and it repels all the other 3 bit strongly. Yeah, this is the lone pair, it will repel other 3 more with more strength. So these other sticks, other electron pairs, will come a bit closer to each other. And again, when we look at this molecule in microscope, we don't see the electron, we just see the atoms. So what we will see is So this basically would be a kind of a pyramid. I think I can draw it. One goes there, one goes there, and one goes there. So it is sort of a pyramid kind of shape, and we call it, it's because it got 3 legs there. We don't see, just remember, we don't see this lone pair. We got a lone pair here, electron, a pair of electrons here, but we don't see that. We only see the atom. So this is your N, then you have H, H, and H. The shape is trigonal pyramid. Okay, then let's look at the last example here. The last example is CO2. We know about the bonding, the electron dot diagram of carbon dioxide, and this is what we get here. Just need to remind you that when we look at electron pair repulsion, we are looking at the central atom. So we look at the electron pairs attached to the carbon, not to the oxygen here. Just was the case with ammonia here. We did not look at the electron pairs attached to hydrogen. We looked at the electron pairs attached to nitrogen here. So we look at here, and if I ask you how many electron pairs do you see, and if you answer 4, you are right. But when it comes to in this VSEPR theory, multiple bond are treated as single bond. So effectively, I will say that it has got only 2 electron pairs for the purpose of VSEPR theory, for the purpose of determination of the molecular shape. So you got 2 electrons, you got only 2 sticks here. So shape would be this. It's a linear shape, and that basically covers the discussion of VSEPR. One more thing I want to make clear here, that we have looked at electron dot diagrams, and we are familiar with structural formula. So structural formula of methane was this, where it was CH4. Water, structural diagram of water was this. Now this structural diagram gives you information, but it can provide you additional information if we show lone pairs as well. When we also show the lone pairs in a molecular, in the structural formula, then we call it valence structure. Likewise, in ammonia, if you want to show, the structural formula of ammonia is this, but we also have, so this is the structural formula, and if we want to write the valence structure, then we also show the spare lone pair as well as with a single stick. Yeah. Okay, so just to sum up electron repulsion theory, I just want you to go through this. The electron pairs in the molecule repel each other and take up positions as far from one another as possible. The repulsion between pairs is in the following decreasing order. So just as we discussed earlier, lone pair repulsion is the greatest, then lone pair, bonded pair, and finally bonded pair and bonded pair. Yeah, so these are the 3 combinations, and this is the weakest combination, that's the strongest combination. Last one is a multiple bond is treated as if it is a single electron pair, and 2 or 3 electron pairs of a multiple bond are treated as single pair, just as we did in case of carbon dioxide. Okay, now I want you to pause your video and try these questions. I see that they're not visible on the screen, so okay, I'll resize it, and I want you to pause your video and try these questions in your exercise book. I'll just be doing one form here, so they should be pretty straightforward. So electron dot diagram of the molecule, we know that This is what it looked like, and then you also need to show other electrons on chlorine. Number of bonded pairs on the central atom. We can see that there are 4 bonded pairs. Lone pairs on the central atom are 0. Shape of the diagram, we know that it will be tetrahedral, so you just need to show it. You got C, you show like this, this. Here I think I'll take this time to show you the convention that is followed when these things are shown. So when you want to show a 3D shape like this in molecules, the bonds which are within the plane of the paper, within the plane of the screen, are shown with a simple straight line. Now the thing which is sticking out of the screen, coming out of the page, is basically shown with a wedge kind of thing. And the thing which is going into the page, which is not in the plane of this screen, but going into the plane behind the screen, you show with a dotted line. So this is the tradition that is used, and I would suggest that you use this tradition. Tetrahedral. And that's where we are going to stop today.